Welcome to lesson 3.2, the proofs of several theorems that we used or that we will be using in proofs and in solving problems. One of them is not a theorem, it's the corresponding angles postulate, and this says if two parallel lines are cut by a transversal, then corresponding angles are congruent. So using this postulate in a proof, I could simply say any sets of the corresponding angles, remember the corresponding angles make the letter F, so 4 and 8, 3 and 7, 5 and 1, or 2 and 6, that any of them are congruent using the corresponding angles postulate. So I could say angle 4 is congruent to angle 8 by the corresponding angles postulate. Now the only reason I can say this is if the lines are parallel. They did tell us that they were. I forgot to mark it. I'm going to mark it. Now I can say that those angles are congruent. By the way, just so you know, vertical angles like 8 and 5 are always congruent with or without parallel lines. 4 and 1 are always congruent with or without parallel lines. So there we see, even in that, sets of corresponding angles. Same side interior angles theorem. This is probably the longest proof in terms of the proofs that we do for these problems for this section. We've been given parallel lines. So in our proof, M is parallel to N for our given and cut by transversal T. So we'll have to put that in our proof. M is parallel to N, T is transversal. That doesn't give us much to go, transversal, much to go off of. And we're supposed to prove same side interior are supplementary. I'm going to pick angles 4 and 6. Now I can't normally, when I'm just doing a problem that I'm solving, I'll say 4 and 6 are supplementary by the same side interior angle theorem. Then I'll set up my equation and solve. But because I'm proving that, I can't go directly to 6. Okay, when we come up with a game plan for this, by the way, we're trying to prove angle 4 and angle 6 are supplementary. This theorem says if the pair of lines are parallel cut by a transversal, then same side interior angles are supplementary. There are only supplementary set with parallel lines other than linear pairs, which are always supplementary. What's in our toolbox? Because of the parallel lines cut by transversal, that doesn't really tell us much in terms of our vocabulary. But that is the conditions for this postulate, corresponding angles postulate. You can't use this postulate unless you've been given parallel lines. Because we were given parallel lines, we can use the corresponding angles postulate. We don't have to prove it, we can just state it. The other things that we can use in our proof, but we don't have to necessarily, are the vertical angles theorem, because there are vertical angles in this picture, and linear pairs. Our goal is to find a way to connect these two angles without connecting them directly. So that's our game plan, kind of like a flight plan. Can't fly directly to Hawaii, so I need to fly to another city first. I don't want to fly to 5 cities to get there. I want to find the most direct route possible. Well, if I'm looking at corresponding angles and I'm starting at 4, its corresponding angle is angle 8. So I have a way or a connector, and that connector to get me from 4 to 8 is the corresponding angles postulate. So that's my game plan so far. I'm going to go from 4 to 8 using the corresponding angles postulate. But I'm trying to get to 6. So some people say, well, use the vertical angles and then go to 6. You could do that, but it's going to add more steps to your proof. There is a direct relationship between angle 6 and angle 8. They are a linear pair. So I can go directly from 8 to 6 using the linear pair theorem. So when I do this, I'm looking at how can I get from 4 to 6 with either corresponding angles, because I have parallel lines. If I didn't have that, I couldn't use this. Vertical angles or linear pairs, I can always use vertical angles and linear pairs. Our first step of this proof is that M is parallel to N and T is a transversal. this is our given statement. From here, I'm saying, hey, I want to go from 4 to 8, and I have a direct path to do that. Angle 4 is congruent to angle 8 because the lines were given as parallel, and I have that in my proof already, so I'm allowed to say that they're congruent using the corresponding angles postulate. Corresponding angles postulate. I can write an equation from this if I want to. I might not need to, so well, we are going to need to. The reason we're going to need to is linear pairs are not congruent, so I'm not going to be able to connect these like a train statement. I'm going to have linear pairs, so I'm going to need equations, not congruent symbols. So my next line will be that the measure of angle 4 is equal to the measure of angle 8. It's coming from the line above that they're congruent, so the reason is the definition of congruent. We have an equation established connecting angle 4 to angle 8. Now our goal is to get an equation from 8 to 6. I can't jump straight to that though. To get from 8 to 6, I first have to write their relationship. The relationship between 8 and 6 is that they're a linear pair, and we know that that means that angle 8 and angle 6 are supplementary. And the reason they're supplementary is because they're linear pairs, so the reason is the linear pair theorem. If you want to identify them as linear pairs first and say that they are a linear pair, then you just have to write by the definition of linear pair, but I usually skip that step. Because they're supplementary, I can say the measure of angle 8 plus the measure of angle 6 equals 180 degrees. The reason, well, the word supplementary. So definition of supplementary. Now I have two equations, one showing that 8 and 6 add to 180, one saying that angle 4 is equal to angle 8. So I can actually plug that in. Measure of angle 4 plus measure of angle 6 equals 180 degrees. I did that by plugging it in, so the reason is substitution. And now that I have an equation saying that 4 and 6 are adding to 180, which is what I wanted, a way to connect 4 to 6, they are now connected through an equation, I can write my final conclusion that angles 4 and 6 are supplementary. Not by the same side interior angle theorem, because that's what we're proving. Normally, I would just say 4 and 6 are supplementary by the same side interior angle theorem. But because of the line above, since they add to 180, they are supplementary by the definition of supplementary. So we knew because of parallel lines that we could use the corresponding angles postulate. We're always able to use vertical angles or linear pairs. In this picture, we found a way to connect 4 to 8 using corresponding angles, and then 8 to 6 using a linear pair. Because of the linear pairs being supplementary, we needed equations, which is why after saying that these were congruent by corresponding angles postulate, we needed to say they were equal in measure. After saying these were supplementary, we needed to say they added to 180, and then we were able to go from there. Proof of the alternate interior angles theorem. If two parallel lines are cut by a transversal, then alternate interior angles are congruent. This picture is set up similarly, but our picture doesn't always have to be like this. Our given is that M is parallel to N for this particular picture, because that's our hypothesis is that the lines are parallel. And T, we'll call it T, is the transversal. A lot of you are looking going, that doesn't help us. It's not like they didn't tell us there was a midpoint or a bisector. We're supposed to prove the alternate interior angles. I'm going to pick 3 and 6, but you could pick 4 and 5, are congruent. What's in our toolbox? If the lines weren't parallel, we couldn't be using what we're about to, but we can use corresponding angles postulate anytime we see parallel lines. We can always use vertical angles theorem, and we can always use linear pair theorem. But we won't always want all of these. We'll want a combination that works for our picture. Starting at angle 3, I would like to connect to angle 6. Now there are two paths I could take to get there that are direct, and a bunch of crazy paths I could take to get there. I don't really want to do linear pairs because linear pairs involve supplementary angles. And I'm trying to prove things are congruent, and vertical angles already have congruent statements. So do corresponding. So some of my students say, well, go from 3 to 7. You could. 3 to 7 is a path using corresponding angles postulate. And some people say that once you're at 7, right, then you can go directly to 6 using vertical angles. That is a very good path using some things that are already in our toolbox. There's an alternate path, though, and that is that I could go from 3 to 2 using vertical angles, and then connect 2 to 6 using corresponding angles. I'm going to take this second path, but both work in a very similar way, so there is more than one way to do this proof. Our first line is that m is parallel to n, t is the transversal. That is given. Next, because I'm going to start at 3 and end at 6, that's what I chose to do. You could have started at 6 and made your way to 3, gone 6 to 7 and 7 to 3 if you wanted, or 6 to 2 and 2 to 3, but I'm starting at 3. So I'm going to say angle 3 is congruent to angle 2 using the vertical angle theorem. Now, if you want to, you can write an equation, but one is not needed here because we're going to have a bunch of congruency statements. So I've already made my connection from 3 to 2. I'm now sitting at angle 2. To fly to angle 6, I'm going to need to use the corresponding angles postulate. Angle 2 is congruent to angle 6 using the corresponding angles postulate. Well, now we started at 3, we went to 2, and now we're at 6. So we've established a way from 3 to 2 and 2 to 6, so we've gone from 3 to 6. This is like taking a mode of transportation. 3 is congruent to 2, and 2 is congruent to 6. So angle 3 is congruent to 6. Now, normally, here's where people get it wrong. They're like, oh, 3 and 6 are alternate interior. I'm going to say alternate interior angles theorem. That'd be great, except that's the theorem we're proving. So we cannot use something that we're proving. It doesn't make sense. Using the statements above, though, 2 is the connector. 3 was our start, 6 was our end. So we used the transitive property of congruence in this case, because they're all congruent statements, to connect these. This would not be substitution. You can only do substitution if you ended up writing that these were equal by definition of congruent, but that's going to add 3 more steps to your proof, or at least 2 more steps to your proof. Our last proof for now, alternate exterior angles theorem. When two parallel lines are cut by transversal, or if they are, then alternate exterior angles are congruent. So in this picture, again, I picked m and n for fun. M is parallel to n, t is the transversal. We're going to prove, now there's 2 sets of alternate exterior. I'm going to do 1 and 8. That angle 1 is congruent to angle 8. See if you can pause the video and come up with a game plan to get from angle 1 to 8. Think about what's in your toolbox. It's the same thing that was in our toolbox both times. The m is parallel to n does allow us to use corresponding angles. We can always use vertical angles, and we can always use linear pairs. Although because I'm trying to prove congruence, I'm probably going to avoid the linear pairs, but it is an option. It just will take a lot more steps. If I'm starting at angle 1, some of you said, well, why don't you go from 1 to 5 using the corresponding angles? That would work. And then 5 goes to 8 using vertical angles. I could also go from 1 to 4 using vertical angles, and 4 to 8 using corresponding angles. I'm going to choose the first path this time. So my first line is that m is parallel to n, t is the transversal. That's our given. I want to connect angle 1 to angle 5. So I'm going to write angle 1 and angle 5 are congruent because they are. They're congruent since the lines are parallel. We can say this using the corresponding angles postulate. Now that we're at angle 5 and 8 are congruent. That's using the vertical angle theorem. And our very last line for this proof, we made our way to 5 and from 5 to 8. So we started at 5, we started at 1, we connected at 5, we ended at 8. So we started at 1 and we end at 8 using the transitive property of congruency. Now I take my time a little bit more when I'm in class doing this, so hopefully we have the ability to do that. If not, I hope, or sometimes you just need this to review, so hopefully this video works as a review for you. What can you assume true if, and only if, the lines are given as parallel? If they're not given as parallel, this stuff's not true. Corresponding angles are congruent by the corresponding angles postulate. Alternate interior angles are congruent, and alternate exterior angles are congruent by their theorems. And same side interior angles are supplementary. Notice they start with S, just like straight angle, by the same side interior angle theorem. The only one that's a postulate now in our repertoire other than segment addition and angle addition is corresponding angles postulate, and that's with the parallel lines. Hopefully you find this video helpful for review. Have a great day.